In this video, we're going to talk about implicit differentiation. And so the idea here is that there are some equations that we might have that we can't solve for one of the variables. So we could have something like x cubed plus y cubed equals 6xy. And in this expression, we can't isolate one variable. So it's impossible here to get x or y by itself. But we may still want to compute the derivative of this. This still has a graph. It's not a function, but you can still graph it. You can talk about tangent lines, things like that. So we want to have an idea for how do we take the derivative in a situation like this. And so what we're going to do is what is called an implicit derivative. So implicit differentiation is the process of differentiating both sides of an equation with respect to one variable, treating all other variables as dependent on that variable. So this is what implicit differentiation means. Basically, it means that we're just going to assume y is a function of x, and so we're going to treat it as some function of x still when we take the derivative. And what you're going to see here is we're basically going to be using the chain rule wherever we see a y or something like that showing up. And so we're going to start with the following example. So we want to find the line tangent to the circle x squared plus y squared equals 25 at the point 3, 4. Okay, so we want to find this tangent line. And so what we're going to do is we're going to take the derivative of both sides implicitly and figure out what dy over dx is by solving for it. And so to see that, the first step is we're going to take the derivative of both sides with respect to x. Now I'm actually going to do the right side first. The derivative of 25, that's a constant, so it's 0. So now the derivative of the left side, we can split this up over addition, is the derivative of x squared plus the derivative of y squared. Now we know how to do the derivative of x squared, it is just 2x. Plus, we need to do the derivative of y squared. And so this is where we are going to treat y as if it is a function of x. And so we're going to do a chain rule here, where our outer function is going to be the squared function because we're squaring y, and our inner function is y. And so if we take the derivatives, the derivative of x squared is 2x, the derivative of y is dy over dx. We've talked about that before, that's just notation for the derivative of y. And so then from the chain rule, the derivative of y squared would be 2, plug in the inner function y, times dy over dx. And so that's what we're doing every time when we're doing an implicit derivative, we're just doing the chain rule. But normally we just think of taking the derivative of the function as if it was in terms of x, and then just multiply it by dy over dx, as that inner function will always be y. But what we have here is 2x plus 2y dy over dx must be equal to 0. And so now we want the derivative, so we want dy over dx, so we're going to solve for that. So we're going to subtract 2x from each side to get 2y dy over dx equals negative 2x, then divide by 2y. So dy over dx is going to be equal to negative x over y. And so this then is the derivative, which was not done, but we have the derivative now. So just like what we've done before with derivatives, this is going to tell us the slope at a point. And so the point we care about is we want the tangent line at the point 3, 4. And so we're going to plug in our point 3, 4. So our slope at 3, 4. Well, we're just going to plug 3, 4 into our derivative. So x is 3, y is 4, so we get minus 3/4. So the slope of our tangent line is minus 3/4. Now we just use point slope form, so we have y minus our y coordinate, which is 4, equals minus 3/4, times x minus our x coordinate, which is minus 3. Oh, it's not minus 3, it's just 3. And so we've got y minus 4 equals negative 3/4 x plus 9 over 4. Then adding 4 to both sides, we get y equals minus 3/4 x plus 9 over 4 plus 4. So we get minus 3/4 plus 25 over 4, minus 3/4 x. And so that then is our tangent line. Now, a circle is a bit of a unique situation, as we could have done this by actually solving for the equation where the tangent line would show up. So if you think of the picture of a circle, it looks something like the following, and our point 3, 4 is up here. So what we did is we found basically the equation of this tangent line right here. And notice a circle is not a function, it fails the vertical line test. But if we just took the top half of the circle, we'd be able to still find the tangent line. And so if we just take the top half rather than the whole circle, we'd have a regular function, and then we could have found the tangent line that way. And so the way we would have done that is we had the equation x squared plus y squared equals 25. Solving for y, we get y squared equals 25 minus x squared. So y equals plus or minus square root of 25 minus x squared. And so now the top equation here is y equals the square root of 25 minus x squared. And the bottom is y equals negative square root of 25 minus x squared. And so we could then use this square root of 25 minus x squared and use it to find the derivative and to find the tangent line and everything like that. And so we're going to do that just so you can see that you do get the same answer. And so we're going to take the derivative of the square root of 25 minus x squared. So taking the derivative, this is the derivative of 25 minus x squared to the 1/2 power. So we're going to use the chain rule. So the derivative of the square root function is just using the power rule. So we're going to have 1/2 times the inner function raised to the minus 1/2. So we brought down the exponent, subtracted 1 from the exponent, and then we multiply by the derivative of our inner function, which is 25 minus x squared. And so now simplifying that, we're going to have 1/2 times 25 minus x squared raised to the minus 1/2 times the derivative of 25 minus x squared is negative 2x. And so we get for the derivative negative x times 25 minus x squared raised to the minus 1/2. So then that is our derivative. So now we care about the point 3, 4. So the slope at 3, 4, we're just going to plug 3 in for x. So we're going to have the m equals negative 3 times 25 minus 3 squared raised to the minus 1/2. So we have negative 3, and then 25 minus 9 raised to the negative 1/2. So negative 3 times 16 to the minus 1/2, which equals negative 3 over the square root of 16, which is negative 3/4. And so notice we got the same slope that we did before. And so we would end up with the same tangent line then. And so it didn't matter if we did it using this implicit derivative method or if we actually solved for y and then computed the slope. But the one benefit of the implicit method is with the implicit derivative, this works for any point. So this works for any point on x squared plus y squared equals 25. And so if we picked a point that was down here in the lower quadrant, we'd have to use a different equation. We'd have to use the lower equation to find the derivative if we did it explicitly, which is just solving for y and then taking the derivative. But implicitly, we'd have the same derivative. And so in some sense, we can simplify our work by taking an implicit derivative in the circle example. So next, let's look at another example. And so we want to find where in the first quadrant x cubed plus y cubed equals 6xy has a horizontal tangent line. Okay, so we want to find out where this function has a horizontal, well, this equation has a horizontal tangent line in the first quadrant. So remember, a horizontal tangent line would mean the derivative is 0 there. So in other words, we want to find where in quadrant 1 dy over dx equals 0 for this equation. So we're going to take the derivative, figure out what dy over dx is to start with. And to do that, we're going to need an implicit derivative. So we're going to take the derivative of the left side and the right side separately. So we'll take the derivative of x cubed plus y cubed and the derivative of 6xy. So x cubed plus y cubed is going to behave basically the same way x squared plus y squared did. So we're going to get 3x squared plus 3y squared dy over dx. And again, I'm not going to write this every time, but again, our outer function in this case was the function x cubed, and our inner function was y. When you're doing an implicit derivative, that's always the case. The inner function is always y, and the outer function is whatever you were doing to y. And so you just take the derivative of the inner function, and then you're going to add on a dy over dx from the chain rule. So now we want to take the derivative of 6 times xy. So this is a product of two things. So we're going to have the derivative of the first thing, which is 6x, times the second thing, plus the first thing, which is 6x, times the derivative of the second thing. Well, the derivative of 6x is 6, so we get 6y plus 6x, and then the derivative of y with respect to x is just dy over dx. And so what we have found then is that we have 3x squared plus 3y squared dy over dx equals 6y plus 6x dy over dx. And so now we want to find dy over dx, so we're going to solve for dy over dx. To start with, there's an easy simplification dividing everything by 3. So we're going to get x squared plus y squared dy over dx equals 2y plus 2x dy over dx. Now we're going to get everything with a dy over dx on the left-hand side, and everything else on the right-hand side. So we're going to subtract x squared from both sides, and subtract 2x dy over dx from both sides. And again, all we're doing is getting all the dy over dx terms on one side. So this gives us y squared dy over dx minus 2x dy over dx equals 2y minus x squared. So now we have a dy over dx in every term on the left-hand side, so we can factor it out. So we have dy over dx times y squared minus 2x is equal to 2y minus x squared. And now we'll just divide. So we get dy over dx must be equal to 2y minus x squared divided by y squared minus 2x. And so that then is our derivative. So we have found the derivative of our function, or our equation, but we wanted to know when we have a horizontal tangent line. And so, in other words, we want to know when is this equal to 0. And so we're going to set this equal to 0. So we have dy over dx equals 0. So this will be 2y minus x squared divided by y squared minus 2x. And we want to solve for when this is 0. Now, assuming the bottom isn't 0, we would have just that the top has to be 0. So in other words, this happens if and only if 0 equals 2y minus x squared. And now we're going to just solve for when this happens and then check that it's in the first quadrant and that the bottom is not 0. If you have the bottom is 0, then we've got a hole in our graph, as we've seen before when we were talking about limits. So we just have to check for that. But rather than worrying about it right now, we'll just check for it after we know what point this happens at. So we have here that 0 equals 2y minus x squared. And so solving then for y, we're going to have x squared equals 2y, or y equals x squared over 2. So now, what this is this is a formula that tells us all of the points where we would get a horizontal tangent line. So every time y equals x squared over 2, we're going to get a horizontal tangent line from a horizontal value from this derivative. But we're going to plug this into our original equation to figure out what x and y actually are. Because remember that our original equation said that x cubed plus y cubed must equal 6xy. So we're going to plug this in for y and then figure out what x has to be. And so we're just solving a system of equations. And so this is equation 1, and this is equation 2. So this is something that you do in college algebra sometimes. And so that's all we're doing here. And so we're going to do our substitution. So we have x cubed plus y, but y is x squared over 2. Cubed equals 6x, and then y is x squared over 2. Okay, and now we have to solve for what x is. And so on the left-hand side, we get x cubed plus 1/8 x to the 6th. And then on the right-hand side, we get 6x cubed divided by 2, which is just 3x cubed. And so subtracting x cubed over, you get 1/8 x to the 6th equals 2x squared. Multiplying by 8, we get x to the 6th equals 16x cubed. So we got x to the 6th equals 16x cubed. Now, we're in the first quadrant. So remember that we only care about the first quadrant, so we can assume that x is not 0. Because we're in the first quadrant, x isn't 0 in the first quadrant. X is positive and y is positive. And so I'm then going to divide by x cubed, which is fine since I know it's not 0. So we get x cubed equals 16. So x is the cube root of 16, which is 2 to the 4/3. And so that is then our x value. So now we need to know what our y value is. So we're going to plug it back into our equation from before, this equation right here. So we get y equals 1/2 x, but x is 2 to the 4/3 squared. So y then is going to be 1/2 times 2 to the 8/3, which is going to be 2 to the 5/3. And so we've got 2 to the 5/3 now for our y coordinate. And so our point where we have a horizontal tangent line with a horizontal tangent line is the point 2 to the 4/3, comma 2 to the 5/3. Now we do need to check that the denominator of our derivative is not 0 there. So we call dy over dx is equal to 2y minus x squared over y squared minus 2x. So we just need to check what is y squared minus 2x at this point. So we'd have 2 5/3 squared minus 2 times 2 to the 4/3. So we get 2 to the 10/3 minus 2 to the 7/3, which is not 0. And so we don't get 0 there, so this is indeed our point with a horizontal tangent line. Okay, now that example admittedly is a little bit on the harder side. Finding the derivative is kind of the key thing here, this derivative that we found. But then checking where you have a horizontal tangent line, it does require you to actually do some algebraic manipulation, which is what we did to find that point. So now let's look at another example. So in this example, we want to find y prime if sine of x plus y equals y cubed cosine of x. So we want to solve this expression for y prime. So we're going to take the derivative of both sides separately. So take the derivative with respect to x of sine of x plus y, and the derivative of y cubed cosine of x. So for the first one, we've got a composition where we've plugged x plus y into sine. So we have cosine of the inner function, which is x plus y, times the derivative of our inner function, which is x plus y. And so this becomes cosine of x plus y times the derivative of x is 1, and the derivative of y is just going to be y prime. I'm just going to write y prime instead of dy over dx now, but it's still the derivative of y. And now on the second one, we have a product rule. So we have the derivative of y cubed, derivative of the first times the second, plus the first times the derivative of the second. The derivative of y cubed is 3y squared y prime times cosine of x plus y cubed times the derivative of cosine is negative sine. And so we set these equal to each other, the two sides equal. So we get cosine of x plus y times 1 plus y prime must equal 3y squared y prime cosine of x minus y cubed sine of x. And so we want to solve for y prime. So we're going to first multiply out the left-hand side to get cosine of x plus y prime cosine of x plus y. And this equals 3y squared y prime cosine of x minus y cubed sine of x. So now we want to get all of the y prime terms on one side. So we're going to add y cubed sine of x to both sides, and subtract off our y prime cosine of x plus y from both sides. And so doing this on the left-hand side, we're going to have a cosine of x plus y cubed sine of x. And this is equal to, on the other side, we have 3y squared y prime cosine of x minus y prime cosine of x plus y. And so this is then what we have got. And so from here, then, we need to factor out our y prime. So cosine of x plus y cubed sine of x equals y prime times 3y squared cosine of x minus cosine of x plus y. Then we're going to divide off our 3y squared cosine of x minus cosine of x plus y from both sides. And so we end up with y prime equals cosine of x plus y cubed sine of x divided by our 3y squared cosine of x minus cosine of x plus y. And so that then is our derivative. And so we were able to compute the derivative of sine of x plus y equals y cubed cosine of x. So next, we're going to compute the following one. So we want to find the derivative dy over dx for e to the x sine of y equals x plus y. So I want to take the derivative of each side separately. So we have e to the x sine of y. And so then we've also got the derivative of the other side, which is x plus y. So the derivative of e to the x sine of y, we're going to have the derivative of the first times the second plus the first times the derivative of sine of y. The derivative of e to the x is e to the x. We get e to the x sine of y plus e to the x cosine of y times dy over dx, because we have to use the chain rule on sine of y. And then for the derivative of x plus y, we did that earlier. This is just 1 plus dy over dx. And so setting those two equal, we have e to the x sine of y plus e to the x cosine of y dy over dx is equal to 1 plus dy over dx. And we want to solve for dy over dx. So we're going to get everything to one side, as we have done before. So I'm going to subtract dy over dx from both sides. And we're also going to move over the e to the x sine of y. So we get e to the x cosine of y dy over dx minus dy over dx equals 1 minus e to the x sine of y. And then we factor off our dy over dx. So we got dy over dx times e to the x cosine of y minus 1 equals 1 minus e to the x sine of y. And so dividing, we get dy over dx equals 1 minus e to the x sine of y divided by e to the x cosine of y minus 1. And so that then is our derivative. So now, as you may recall, before we've talked about this idea of second derivatives and higher order derivatives. You can do higher order derivatives with implicit differentiation the same way that we've done it before. And so we're going to look at an example of doing that now. So we want to find y double prime if we have x to the fourth plus y to the fourth equals 16. And so what we're going to do is we're going to first take the first derivative of each side. So we take the derivative of x to the fourth plus y to the fourth, which is 4x cubed plus 4y cubed y prime. And we take the derivative of 16, which is 0. And setting these equal then, we've got 4x cubed plus 4y cubed y prime equals 0. So 4y cubed y prime equals negative 4x cubed solving for y prime, we get negative x cubed over y cubed. And so this then is our first derivative. So we've got the first derivative now, it's negative x cubed over y cubed. But we wanted the second derivative. And now we don't even really have to worry about the fact that we've got a mixture of things. We're just going to take the derivative of both sides. And so if we take the derivative of y prime, we get y double prime. And so we've got y double prime on the left now. If we take, I guess I should write this down. Okay, so now to get y double prime, we're going to take the derivative of both sides. So the derivative of y prime is y double prime. So we've got y double prime on the left. And on the right, we have a quotient rule. So we're going to take the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. So we're just using our quotient rule from before. So let's actually compute these derivatives. So the derivative of x cubed is going to be negative 3x squared y cubed. Then we're going to have plus x cubed times 3y squared y prime divided by y to the sixth. Okay? And so we're just taking the derivative as we have done before. The derivative of y cubed is going to be 3y squared y prime using the chain rule. And so this then gives us negative 3x squared y cubed plus 3x cubed y squared y prime divided by y to the sixth. So now at this point, we know what y prime is. Remember, y prime is that equation we found before. It's minus x cubed over y cubed. So we're going to plug that in. So the second derivative, y double prime, equals negative 3x squared y cubed plus 3x squared y x cubed y squared times y prime. Y prime is negative x cubed over y cubed divided by y to the sixth. So now we are just going to simplify this. Okay, so this is the second derivative, but we want to simplify it to make it easier to work with. So I'm going to multiply the top and the bottom by y cubed, just to make it so we don't have a mixed fraction on the top. So we got y double prime equals negative 3x squared times y to the sixth, because we're multiplying by y cubed, plus 3x squared y squared x cubed y squared times negative x cubed. We multiplied by y cubed, so those cancel. And so I am distributing this y cubed to both terms over the addition. And then on the bottom, we're going to get y to the ninth, just adding exponents. So this becomes negative 3x squared y to the sixth plus, rather minus 3x to the sixth y squared divided by y to the ninth. So now notice here that we have a y, some y's on both the top and the bottom. So we're going to factor that out. So we have y squared that we can factor out of everything. So we're going to have y squared times 3x squared y to the fourth minus 3x to the sixth divided by y to the ninth. And we can cancel off two of those. So this gives us negative 3x squared y to the fourth minus 3x to the sixth divided by y to the seventh. But notice we can actually factor this even more. And so we have this a 3x squared we can factor out of everything, or rather a negative 3x squared. So y double prime equals negative 3x squared times y to the fourth plus x to the fourth divided by y to the seventh. And now, you may or may not remember, but we actually know what x to the fourth plus y to the fourth is. Remember that x to the fourth plus y to the fourth is 16. That's just the expression that we had to begin with. And so we're just going to plug 16 in for it, because that's what it equals. So this equals negative 3x squared times 16 divided by y to the 7th. And so we get then that y double prime is equal to negative 48 x squared over y to the 7th. And so that then is our second derivative.